Hi guys, this is a quick video to help you understand and cover the unit system software, specifically section 5.2, which will be about things like program libraries and language translators. So let's get on to it, starting off with our first lesson, which is going to be on program libraries. And remember, program libraries, and in the next lesson, we study about language translators. They're all studied in the second part of system software. You can think of it as system software, Unit 5, Part 2. What are program libraries? Now, first of all, when you write programs in Python, C++, Java, whatever the language you guys prefer, you may encounter a situation where you may import code that someone else has written. What does that mean? Now, a perfect example of this is in Python. If you guys wanted to calculate the sign of a particular number, when I say sign, I mean sine, cosine, tan, I mean the sign in trigonometry, right? Imagine you want to calculate the sign of 15. How would you calculate the sign of the number 15 or 15 degrees, for instance, in Python? You can't really implement this yourself. You might have to import code that someone else has written for you to be able to calculate the sign of 15. Now, when I say you can't, I'm not saying that it's impossible. You could, if you learn about the theories and the respective methods of calculating sign. There are algorithms that you can use to calculate the sign of a value. So you can, if you wanted to implement everything by yourself, you can go and implement your own sign function. But frankly, there are programmers that have already understood how the sign function works and have implemented the sign function for you, which you can then import directly into your program in Python, for example, and just execute it. And the way you do this in Python is by saying import math, right? Which is the library name in Python. Math is the library where you have a lots of functions that you can reuse in your code, specifically related to mathematics, also related to trigonometry, calculus, and whatnot, right? So you can import the math library, and you could do math dot sign 15, where when you import the math library, this library is full of code related to mathematics that other people have written for you, right? The developers of Python have written a program library called math, which contains all these mathematical functions, which you could directly reuse in your program by simply saying math, which is the library name, and sign, which is the function name. So the idea is, guys, by importing math, you're importing something called a program library, where program libraries are pre-written, reusable sets of code that developers can include in their very own programs, right? Such as you importing math to include the sign function in your own program. And program libraries are not just one or two functions, it's over 50 to 100 functions that you can directly use in your programs. And they don't only contain functions, they contain functions, procedures, classes, as well as constants. All of these things may be provided to you by the program library. In this case, the math library provides functions for sign, procedures for other functions that might be mathematically related. It provides classes for you to work with mathematical functions. It also provides constants like pi or e. It provides fairly accurate constants for you guys to directly use them in your program without having to, implement pi or create a constant for pi and e by yourself. So all you have to do to use the constant pi in the math library is just to say math.pi, right? I believe this may be spelled with capital Pi. You might have to double check that, but the idea is that you can import all these things, functions, procedures, classes, constants, and other people pre-written code that other people, like I said, have written that you can reuse in your own program. So the most important thing about program libraries is that rather than writing everything from scratch, developers can import code from a library, such as the math library in Python, to handle standard tasks like sorting, file handling, or arithmetic operations. That means you don't have to waste time implementing those basic algorithms. All you have to do is import stuff from other code from other libraries, and you can focus on solving the problem that you want to solve without being bogged down by these basic algorithms. Hopefully that makes sense to you guys. This is a general introduction to program libraries. Now, what are the overall benefits of program libraries, guys? It saves development time, definitely. You don't have to reinvent common solutions. Do you have to learn about how the sine function is implemented and implement it yourself? No, just go ahead, import math, and then say math.sine. Encourages modularity. Basically, your programs become modular. You are reusing other people's programs, you're reusing other people's code, and you're reusing other people's functions and procedures, which makes your program a bit like plug and play, where you can always reuse code. You can always make your programs modular, which means to essentially break your program down into small parts and reuse those small parts. So by using program libraries, you're encouraging modularity, where the code is now broken down into snippets that each have a specific task. The math.sine function does the sine calculation. Math.tan calculates the tan. Likewise, each function has a specific job. So you're encouraging modularity by reusing existing functions. So programs become cleaner and more organized. Improves reliability. Now, see, if you think about the sine functions, implementing the sine function yourself might be good. It's a good opportunity for you guys to learn how the sine function works. But here's the thing, right? If you think about your implementation of the sine function and a sine function that is implemented by a programmer that came before you, frankly, you need to understand that the programmer that came before you may have implemented the sine function with more knowledge and have also, supplied the sine function. It has the programmer that came before you that implemented the sine function may have subjected it to a lot of tests to see if the sine function behaves well, even for erratic or sort of erroneous values or for boundary values as well. So the idea is that, it's always good for you guys to try and implement things by yourself, but you don't have to reinvent the wheel, because sometimes you may make errors when you implement code entirely by yourself, which you could have used other people's programs to replace with. So libraries are a very good way to often use tested and maintained code which you are sure that runs, right? It improves the reliability of your own programs if you reuse ones that were made by others, because those programs are essentially tested well. Then simplifies collaboration. Developers can focus on their domain while reusing general purpose logic. You don't have to focus on learning the branches of mathematics and the entire subject of data structures and algorithms just to be able to implement a simple application. You could reuse something that other people have written, so you don't have to reinvent the wheel, and you can focus on solving your problem in your domain rather than repeating and re-implementing all these general purpose logic by yourself. So it simplifies collaboration between programmers as well, and essentially helps you build what you want rather than being bogged down by every single thing of a program. So 4 major advantages: saves development time, encourages modularity, improves reliability, and simplifies collaboration. Now, there are 2 major types of these so-called program libraries. One is called static link libraries, or SLLs, and the other is called dynamic link libraries. Now, let's understand what these so-called static link libraries are, guys. Now, what do you think static link libraries are? Static link libraries are libraries that are linked to the program at compile time. That means when the program that you write is compiled, at that time, these libraries are linked to the program. The code from the library is copied from the library into the final executable. So you are not really creating a reference to the code for the library. You're actually literally copy pasting the code from the library into the final executable. Now, keep in mind, you aren't the one that's literally copy pasting it. When you import code from a static link library, when you compile it, the compiler, along with another software called the linker, is the one responsible for copying the code from the library and pasting it into your sort of final program and creating that final executable. And the resulting exe or program file is self-contained. So you don't have to worry about any external dependencies. Now, let me take you through an example of a static link library in action with a nice program and a nice app, a script that you might write in real life, just to explain to you how these SLLs work, static link libraries. Now, here's the idea, guys. Static link libraries are mainly relevant, along with these dynamic link libraries, are mainly relevant when you write programs in languages like C or C++. So don't worry, this is still relevant to Python, but it's more relevant and more easily understood when looking at other programs. So programming languages, beg your pardon. So as a result, let's take a look at how SLLs work with regards to C++, shall we? So let's say that you write a program in C++, and let's say you save your C++ program as main.cpp, right? So this is your own source code. This is your own source code. I hope that's clear with you. This is your own source code. Now, let's say in this program, you're calculating the tax of some price or some amount of money. Maybe you're building like a financial software in C++, and you are trying to calculate the tax of something. And frankly, to calculate the tax, you haven't implemented a function or procedure by yourself. You are borrowing a function or procedure that someone else has implemented in a different static link library. So let's say that in your main.cpp program, you are using a function called calculate tax. Now, have you implemented calculate tax? No. You have implemented calculate tax from a SLL, a static link library. So in main.cpp, therefore, in the C++ file that you have written, you have your own source code, and you're also calling this library program. So that means that you are not implementing calculate text by yourself. You're just calling the calculate text function that has been implemented in this static link library. So you're just calling the library function, reusing or using that defined already in the static link library. So you can imagine that the static link library is a library that contains tax-related calculations. This static link library is a library for tax calculation. So all tax calculation related functions are already implemented in this static link library, right? Okay, so now you've written main.cpp using the calculate text function that has been already implemented in a different static link library. Now, the process from this point on is pretty straightforward, right? Now, we know that main.cpp has to eventually be converted into machine code. It has to be converted to machine code, which is binary, in order for main.cpp to be able to run in your CPU. So main.cpp is C++ source code, but it has to eventually get converted into machine code, which is binary. Now, in order to convert this main.cpp into binary, we need to use a kind of translation software called a compiler. We will study about the compiler soon in this lesson itself under language translators. But the idea is that main.cpp has to be converted into binary using a compiler. Now, what the compiler does is it takes this main.cpp file and converts it to machine code, but while or during the process of compilation, right? Maybe I can put a star mark here and say that if I draw this box again, consider this box to be the compiler, guys. Consider this box to be the compiler. While it takes in your C++ program, it also takes in the calculate tax function from the static link library, right? So it takes your C++ source code and along with that, it also takes a copy of the calculate tax function, copies library function, right? And what the compiler does is the compiler combines this source code and this copy of a library function into a final executable, right? So in essence, what happens with static link libraries is that when you call a library function from a static link library, the compiler has a responsibility of combining your source code with a literal copy of that function embedded within that source code. You understand that? As a result, you end up with an executable that is standalone. It is one final self-contained exe that has no external dependency, right? So the calculate tax function was implemented in a different static link library, but the fact that you've now compiled it means that a copy of that now exists in the final source code. Not that it's visible to you, but it's embedded together in the final executable. So the final executable, therefore, no longer needs to refer to this static link library because it's literally a copy of the calculate tax function, but in the single executable itself, right? And I want to make one more clarification here, guys. The compiler does compile the source code into executable, or specifically there's a small nuance that compiles into object code. So you can imagine that the compiler's job is just a bit less complicated than this. It compiles C++ programs or any programming language for that matter into object code. But the final process of copying the library function into that object code and forming that final executable is actually done by a process or a software called a linker. So you can imagine that if I were to quickly edit this just to make it a bit more precise, let's see. Let me just quickly get rid of this. It does take a bit too long to erase. Why is this? Okay, perfect. Yeah. So you can imagine that the C++ source code is passed into the compiler, which is the same compiler we drew here, right? The same thing. But it produces an intermediate code called the object code before the final executable, just like what we studied under the two-pass assembler, right? And this so-called object code passes into a different software called a linker, just to be very precise, which is what combines the copy of the static link library program into that object code and forms the final executable. So keep in mind, there's actually two steps here. The compiler compiles your source code into object code, and then the object code is combined with the tax calculate function from your static link library by the linker to produce the final executable, which can then run standalone in your computer. So hopefully that makes sense to you guys. In essence, a program is linked to a static link library function or procedure at compile time, where the code is copied from the library literally into the final executable, resulting in a single self-contained executable with no external dependency. All right, the process of this you need to understand. So if you have any questions, do let me know. Then we have dynamic link libraries. Dynamic link libraries link to the program at runtime, not during compilation. So they don't combine as a copy with the program. There's only a reference that is activated during runtime. The executable itself, like I said, contains references to this dynamic link library, but not the code itself. Therefore, the DLL must be present when the program runs. That's the idea. Now, shall we take a look at exactly how DLLs work and how they're different to static link libraries, guys? Now, imagine you're writing your main.c++ program again. And let's imagine that you're still building that financial software. And here you have your source code along with the calculate text function, but this time the calculate text function you are calling not from a static link library, but from a dynamic link library, DLL, right? So the calculate text function comes from the DLL, It doesn't come from a SLL. It doesn't come from a static link library. It comes from a dynamic link library. Now what happens here is, as usual, main.cpp is compiled through a compiler, right? It's compiled through a compiler. And what you produce is object code. You end up producing object code. But the thing is, this object code right now has no reference to the calculate text function by itself. Therefore, what happens? This object code is then passed into the linker, which does a very specific job now, doesn't do the same thing as the static link library, it does a different thing. Now with the object code and the DLL, the linker combines them in such a way where the linker produces an executable. But the thing with this executable is, does it have a copy of the calculate text function with the DLL? No. It only contains a reference to the calculate text function from the DLL. And so when the program runs during runtime, the CPU or the operating system has to associate that reference from the actual DLL to the runtime. So what that means is that the DLL is a separate file that exists at the beginning, which is where the calculate text function is imported from. But when it's compiled, the object code that is produced by the compiler does not have any reference to the calculate text, so-called by library program or the library function. So what happens is the linker has to then take the responsibility of taking that object code and combining it with the DLL, but not combining it literally, but just essentially creating a reference to the DLL by using some memory address or some kind of memory reference without actually copy pasting the calculate text function from the DLL to the final executable. So the object code is combined by the linker, and there's a reference to the DLL established by the linker whenever the calculate text function is called in your source code. As a result, when the executable runs when the executable runs in the computer, the OS has to then resolve that reference by talking to the DLL during runtime. So the DLL is therefore something that must be present when the program runs. Unlike earlier, where the SLL is present before the program runs, it's compiled, and then the SLL's code is copied to the executable. Therefore, after that, the SLL is no longer required. Whereas DLLs are required to establish the reference during the linking stage. But since it's only a reference, it's also required after, during runtime, to actually be able to call the function during runtime, right? Because it was only a reference. Hopefully this makes sense to you guys as well. So DLLs establish references to library programs. SLLs literally copy paste the library program. So as a result, SLLs produce a standalone executable, whereas DLLs produce an executable that still requires a reference to the program. Now, finally, you end up with SLLs and DLLs. As a quick summary, let's quickly discuss the differences between the two. The first thing about SLLs is that they are linked during compile times, whereas DLLs are linked during runtime. The file size of SLLs is larger, meaning SLL generated code is quite large because they have to literally copy paste the program. Dynamic link libraries are quite small, right? Because the overall final program only contains your source code, but only references to the DLL code. As a result, no, you're not copy pasting the code from the dynamic link library to your program. You're only maintaining references. So you're not bloating your code with code that other people have written. You're only establishing references. Performance-wise, SLLs are slightly faster because you don't have to look up or refer to another library, because during compile time, the SLL has already been copied to the executable. So during runtime, the SLL is no longer required. There's no lookup. Whereas DLLs have a lookup. During runtime, you have to look up the DLL from your hard disk drive and resolve that reference, which takes some time. SLLs are not easy to update, or code that require SLLs are no longer not easy to update, because if the library program that you're using updates, you have to recompile the program, because in SLLs, you're supposed to literally copy paste the program from the static link library to the um, source code. Since you're copy pasting before runtime, during compile time, as a result, what happens is that if you want to update that library program, if you want to use an updated version, or if you want to replace it with something else, you're supposed to recompile the program. Whereas with dynamic link library, since there's only a reference to the DLL, it's very easy to swap the DLL with something new. Memory usage of SLL related code is very high because there's always a duplicate copy of the program in the SLL, which is what makes the executable independent. Whereas DLLs have a lower memory footprint because, the actual code itself is very concise. It's only the code that you've written, and all the other dynamic link library code are references to those library code, not exact copies. A static link library code is more portable because you have a copy. As a result, you no longer need the static link library during execution, whereas DLLs require the DLL file to be available. Therefore, static link library code is better for embedded systems and CLI-based tools because they need to run independently and portably, whereas dynamic link libraries are good for GUI apps and for OS-level features that are okay with using DLL files, dynamic link library files that exist during runtime. That's a quick comparison between the two. Do remember these points and do remember the process through which SLLs and DLLs work. But if there are any questions as usual, do let me know. Now we get to the next part, which is about language translators. Now, language translators is a very interesting section because we learn about how exactly our source code gets converted to machine code, some of which we also referred to when we learned about compilers in the earlier section, right? Language translators are system software. But what do? They convert human readable code into machine code that the computer can understand, because computers can frankly only understand binary, which is why we need language translators. Now, the first kind of a language translator that we have is the assembler, which converts assembly language into machine code. We discussed about assemblers in quite a depth, where we understood about something called the two-pass assembler in the previous unit, isn't it? So this is the same thing. This is just the common name for the two-pass assembly. It's just an assembler, right? It converts assembly code into machine code, where each assembly instruction maps to a single machine instruction. And we saw that with our beautiful two-pass assembly process. Each line of assembly code, like LDD50, LDD20, converts into a single machine instruction. Output is typically an object file on executable, right? The assembler produces an object file on an executable, and the use cases of assemblers are mainly for low-level system programming, embedded systems, and device drivers. Hopefully, you can refer back to our two-pass assembler lesson. You can refer back to our unit 4.2 lesson just to revise this, but hopefully this makes sense to you. Now we come to the compiler. This is the big guns, the ones that do the more complex tasks. The compilers translate entire high-level programs like C and Java into machine code before execution. They translate entire high-level programs into machine code. So not assembly, they translate high-level programs into machine code. And the result of this is a standalone executable file. Compilation happens once, the program can run multiple times. And as far as a compiler is considered, there are several advantages. Number one, it leads to faster execution because the code is already translated. You translate the code and then run it. You don't translate line by line as in a interpreter. It's good for distribution. This is a very, 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 very important point because they sometimes at the exam ask you what choice is better for a particular situation. Is it a compiler or a translator or an interpreter? A compiler is always good for programs where the source code doesn't need to be shipped with the final executable. With compiled programs, you need to only ship the executable, not the source code. So it's really good for distribution because otherwise people can see what your source code is. All games, applications, most systems that you guys purchase, applications that you guys download are all compiled. They don't share the source code with you. They just give you the executable that you can double click and run. Disadvantages of compilation is because it takes time to compile, because it has to compile the entire thing. It takes some time, and it's hard to debug because errors are shown at the end of the full translation. It doesn't show you errors line by line as like in Python. It shows you all the errors at the end if the compilation fails. So advantages, fast execution because the entire code is already translated, and it's good for distribution, but it takes time to compile and it's hard to debug. Interpreters is the opposite of compilers, that they do the same thing. They translate high-level programs into machine code, high-level into machine code. But the problem with interpreters is that, or not rather the problem, but the feature of interpreters is that they translate and execute code line at a time, line by line. Meaning, unlike a compiler which translates the entire program at once, interpreters translate and execute the lines one by one. But keep in mind, it doesn't only translate one line at a time, it translates while executing those lines one by one. And Python and JavaScript are both examples of interpreted languages. As a result of executing the line one by one, there is no immediate exe file that is created. So that is a very important thing. If an executable is not required, an interpreter is a good choice. But if an executable is required, an interpreter cannot help you out there. Interpreters are really good for rapid development because it allows you to run your program line by line immediately, and it's also really good for testing. Advantages of interpreters are that they provide immediate feedback when an error occurs. If you have errors in line number 1 and 3, you cannot get to line number 3 unless you solve line number 1, which makes it less of an information overload for you because you're solving your errors line by line. Then it's easier, therefore, to test small sections of code. But the disadvantages of an interpreter is that it's slower to execute because it executes line by line, showing you errors one by one. And it requires the interpreter software to be present during runtime, which is not suitable for secure code distribution. Now, compilers compile the code, produce the executable, and then they ship it. So it's time for you to then double-click the executable and run the program. But interpreted programs, like those that you write in Python, cannot be converted to an executable. So what happens is that you need to provide the Python code to the end user, and they are supposed to interpret it by themselves by installing an interpreter on their computer, which is a very difficult task for the general user to do. So we never use interpreter for code distribution or essentially shipping purposes. We don't use interpreted code for end user applications. Finally, a quick comparison between compilers and interpreters. Translation, compilers translate the entire program at once, interpreters line by line. Compilers do fast compilation, they translate the entire thing very fast, and interpreters are slow because of, again, a line by line translation. Compilers execute and show you all the errors at the end. As a result, you'll see an entire list of errors, which is very difficult to debug. But interpreters show you the errors line by line. So therefore, if you encounter errors earlier on in your program, you will have to solve them before you move on to the next few lines. Use cases of compilers are for all production applications, all production apps that have to be shipped to the end user. You use compilation. And for performance tasks, for high performance applications, you use compiled programs as well. Interpreters are better for simple scripting purposes, for learning, and for testing. Compilers output an executable file, very important. Interpreters output no file because the code runs through the interpreter. Compiled programs are less portable because what do the compiled programs produce? They produce an executable file. But the problem with the executable file, guys, is that executable file only works on a specific machine. So this is machine independent. So the executable file that you generate for your Mac device might not work on a Windows machine. So therefore, compiled programs are less portable. Interpreted programs are highly portable. They're highly portable because you have to give the source code to the end user and they can run anywhere they want as long as the interpreter is installed. That's what makes interpreters highly portable. That's the difference between compilers and interpreters. Hopefully that makes sense to you guys as well. All good. Finally, we're going to learn a bit about this very interesting middleman in this story called intermediate code. Now, what's intermediate code? Intermediate code is a translation step between source code and machine code. What does that mean? It's basically a process where you don't translate your source code directly into machine code as in like a compiler or an interpreter. You translate your source code into this intermediate code and then to machine code. Now, you might be wondering why this is even done. It's designed so that the code you produce is platform independent, and it's often used in languages like Java and Python. Now, just to give you an idea of this, machine code I told you just a second ago, that machine code is machine dependent. Machine dependent. Let me show you. I hope I wrote it in the previous. Oops, I think I made a small mistake when I wrote this. I meant to say machine dependent, guys. Compilers produce executable files that are machine dependent, not independent, machine dependent. So, like I said, I think I verbally said it right, but I wrote the wrong word. The idea here is that executables that you produce are only able to execute in a specific system or a specific architecture. They don't work in all computers equally. That's the problem with machine codes. They are machine independent. They are machine dependent. They only run on a specific kind of system. Now, if you want your source code to not be distributed, but you also want your machine code to be machine independent, you're fighting a losing game without using intermediate code. So you guys hopefully understand the idea, right? Source code usually shouldn't be distributed because the end user will then get to see what code you have written. If you don't want to distribute your source code, but also want to get a machine or platform independent version of machine code, that's where intermediate code shines. So again, the reason why we have intermediate code is because we don't want to share our source code, and because machine code is inherently machine dependent. So we have this layer in the middle that is the best of both worlds. It doesn't it helps us share our programs with the end user without sharing the source code, but also make our programs platform independent, which means it can run anywhere as long as it's in intermediate code form. So the benefits of intermediate code is that it allows the same program to run on multiple operating systems without recompilation. It enables optimizations to happen before converting to machine code, and it supports secure and sandboxed execution through softwares like the Java Virtual Machine or the .NET CLR. Again, you don't have to remember the JVM or the .NET CLR or what they mean. That's not part of the syllabus. But you do have to understand that using intermediate code allows you to run the code in a nice protected virtual environment without affecting the hardware at a physical level. So those are the benefits. The main benefit being that the code is platform independent. It can run on multiple operating systems without recompiling. Now it's time to understand how this actually works, and we can understand this by looking at how Java works. Java is a very interesting language because it uses exactly this process of intermediate code. So let's take a look at this, guys. How Java does its job is as follows. First, you write your source code in a .java file. In a .java file, you write your source code, right? You write your source code in a .java file. And then what happens? Java has a compiler called the JVAC or JAVAC. This is called the Java compiler. Now, the Java compiler, based on the definition of the compiler, should hopefully produce machine code, isn't it? Because the compiler produces machine code, we are hoping the Java compiler also produces the machine code. But frankly, the Java compiler produces something called bytecode. It doesn't produce machine code. This bytecode is our intermediate code. I hope that makes sense to you guys. This is the intermediate code. Now, Java, as a result of producing this bytecode, allows this bytecode to run on any machine. But the idea here is that even though bytecode is machine independent, it still needs something called the JVM or the Java Virtual Machine to then convert this bytecode into machine code. Therefore, guys, Java is a prime example of intermediate code generation, where Java code is compiled into bytecode by the Java compiler, which can then run independently of the platform. But in order for the platform to run the bytecode, it needs installed in it something called a Java virtual machine, which can then at runtime convert the bytecode into machine code and thereby run it on the computer CPU. So the Java system is something that you can take away as a good example of intermediate code generation and how it works in real life. But Java system, the system that Java employs, the Java compiler followed by the bytecode process followed by the JVM, that process offers three major features or four major features followed by their benefits. It makes the code portable, which means you can write your code once and run anywhere as long as that anywhere has the JVM installed. It's secure execution because the bytecode is sandboxed by the JVM. The JVM, the Java virtual machine, protects the bytecode and runs it in a secure enclosed environment instead of running it in the physical hardware. Java code, specifically bytecode, is optimizable. What that means is that you could take the bytecode and further optimize it via the JVM during runtime using something called the just-in-time or the JIT compiler or the JIT process. Basically, the JVM is a Java virtual machine that is able to optimize the bytecode during execution. And that makes your code more performant as well. And Java code, especially the bytecode that you produce, has a smaller file size than native executable files or native binaries, we say. So that is how Java works. Now, do you have to ever understand how Java works for the exam? No. But you do need to understand how to explain the process through which intermediate code might be generated. And it's really helpful to see this in action through an actual example, which is why I took Java. And you need to also understand the pros or the advantages of doing this. This concludes System Software Part 2. That's Unit 5, Part 2. If you have any questions as usual, do let me know, and the best of luck for your exams.